Hello guys! In this lecture, we are going to talk about feature engineering. Feature engineering plays a key role in big data analytics. Machine learning and data mining algorithms can't work without data. Little can be achieved if there are few features to represent the underlying data object. And the quality of results of those algorithms largely depends on the quality of the available features. Data often exists in various forms, such as images, text, graph, sequence, and time series. A common way to represent data objects for data analytics is to use feature vectors. Data in raw formats, such as those we said before, are not described by informative features. Even data represented by features vectors may still be in need of new effective features. Feature engineering is concerned with meeting the needs in generating and selecting an effective feature vector-based representation of data, resulting in improved model accuracy on unseen data. There are many types of feature engineering. The first one is feature transformation. Feature transformation is about constructing new features from existing features. This is often achieved using mathematical mapping. In this course, you are going to learn 4 types of feature transformations: label binarization, label encoding, one-hot encoder, and automatic data transformation. The second type of feature engineering is feature generation. Feature generation is about generating new features that are often not the result of feature transformation. For example, we can generate new usable features for images from the pixels of that images. In this course, we are going to learn 2 types of feature generation. The first one is manual feature engineering, and the second is automatic feature engineering. The last type of feature engineering is feature selection. Feature selection is one of the core concepts in machine learning, which hugely impacts the performance of your model. The data features you use to train your machine learning models have a huge influence on the performance you can achieve. Irrelevant or partly relevant features can negatively impact model performance. In this course, we are going to learn 4 types of feature selection: univariate feature selection, feature importance, model-based feature selection, and recursive feature elimination. Let's start with feature transformation. The first method we are going to learn is label binarization. Label binarization converts multi-class labels to binary labels to represent if a class belongs or does not belong to a class. For example, we have a vector of feature values 1, 2, 6, 4, and 2. Now, after applying label binarization to this vector, the value 1 is now represented by a vector 1, 0, 0, 0. And the value 6 is now represented by another vector 0, 0, 0, 1. The second and third type of feature transformations are label encoding and one-hot encoder. We talked about them in the pre-processing section. The final type of feature transformation is automatic data transformation. We are going to talk about PCA. Principal Component Analysis, or PCA, is a dimensionality reduction method that is often used to reduce the dimensionality of large datasets by transforming a large set of variables into a smaller one that still contains most of the information in the large dataset. Now, the benefits of PCA are: first, reduce the number of variables, which will speed up our machine learning model. Second, ensure that our variables are independent of one another. And finally, we use PCA for data visualization. We see in this example how PCA converted 3D feature vector to a 2D feature vector. Now let's talk about feature generation. We have 2 types of feature generation. The first one is manual feature engineering. Manual feature engineering is creating new features from our existing ones to improve model performance. For example, Let's say that we have a dataset for a store, and one of the features is date of customer purchases. Manual feature engineering, in this case, can be to create 3 new features out of this one. These new features are day of purchase, month of purchase, and year of purchase. These new features might increase the accuracy of your model results, and we will see how to manually generate other types of features in another video. The second type of feature generation is automatic feature engineering. We will talk about DFS, or Deep Feature Synthesis. DFS is an automated method for performing feature engineering on relational and temporal data. Let's say that we have a dataset for customer transactions. Unfortunately, this dataset has only 4 features: customers, products, transactions, and session. Typically, without automatic feature engineering, a data scientist would write code to aggregate data for a customer and apply different statistical functions, resulting in features quantifying the customer behavior. In this example, an expert might be interested in features such as total number of sessions or month the customer signed up. These features can be generated by DFS. In this example, we have 4 features, and after applying DFS, we have now 3 new features out of our original 4, and they are count of sessions, month of join date, and month of date of birth. These new features have a huge opportunity to increase your model accuracy. Finally, the last type of feature engineering is feature selection. We will learn 4 techniques we can use to do feature selection. The first one is univariate feature selection. Univariate feature selection works by selecting the best features based on univariate statistical test. The second type is feature importance. Feature importance gives you a score for each feature of your data. The higher the score, the more important or relevant the feature is towards your output variable. The third type of feature selection is model-based feature selection. Model-based feature selection is a method transformer that can be used along with any estimator that have a coefficient or feature importance attributes. The features are considered unimportant and removed if the corresponding coefficient or feature importance values are below the provided threshold parameter. The final type of feature selection is recursive feature elimination. Given an external estimator that assigns weights to features, recursive feature elimination selects features by recursively considering smaller and smaller sets of features. First, the estimator is trained on the initial set of features, and weights are assigned to each one of them. Then, features whose absolute weights are the smallest are eliminated from the current set of features. The procedure is recursively repeated on the set until the desired number of features is eventually reached. So that's it for today's video, and see you in the next one.